Now, computer representation of graphs. Now, we all know the common method that we use to represent graphs, other than drawing a picture or just listing the vertices and edges. We can do so, but we have other approaches that we can also go by. Represent graphs in a computer. There are some of the common methods or approaches. One, the adjacency matrix. You can get represent graph by using the adjacency matrix of a given graph. Two, we can also have the incident matrix, and then we have the adjacency list. The adjacency list. So these are some of the ways you can also represent graphs. So these methods lead to widely used computer representations of a graph. So the above methods we can use to represent graphs in a computer. So let's start with the first one, the adjacency matrix. The adjacency matrix. Now you know what a matrix is, since you are doing the linear algebra. So you know what a matrix is. Now assuming if you are having an integer n and m, a matrix A of size n by m is a rectangular array of values organized as n rows and m columns. This is just a simple, let's say, definition of a matrix. And you know it already because you are doing the linear algebra. Okay. So if you have a matrix, you can even locate a particular entry. Let's say AIG. AIG. I can even write it like using the lower case like A, then we have IJ, something like this, which is not telling you that you want to get from the I flow and J column where the two lines meet, the I row and the J column. At that intersection, what value is there or what entry is there? So assuming if I have A1, 2, there's in the first row, second column, what entry is there? So you can locate the various entries in a given matrix. You know all of this one and the linear algebra. Is it okay? Peter, are you okay with that?
Yes, sir.
Yes, sir.
Good.
Yes, sir. Yes, sir.
Now we are going to use this idea in graphs. That's why I just flash it through the matrices, because we are going to form matrices. Now let's go to the graph. Let the graph G, which is equal to VE, you know the meaning of that, be a graph with n ordered vertices named V1 up to Vn. So we have the vertices of that G as V1 up to Vn. Then we can form a matrix that will be n by n matrix, where entry I, J are the numbers of paths or edges between vertex Vi and Vg. What we are saying here is that if you have a graph with a vertices V1 up to Vn, then we can form a square matrix using the vertices. Now, all what we have to know is that we want to find if there's a connection or there's an edge between two given vertices. You know that if edge, at the end of every edge, there should be what? A vertex. Or the both ends will have vertices. Therefore, we want to see from all the vertices that we have, when you take any two of them, is there any connection? Is there any edge that connect them? If yes, then we name it. How many are they? If it's one, then we name it 1. If there are 2, we name it 2. If there are 3, and so on and so forth. Are you okay? But if there's no edge that connects two given vertices, then we just give it 0. I will keep on doing for all the various vertices within the given graph. Then that's why we form the adjacency matrix. So for adjacency matrix, we deal with the vertices. The vertices. Okay. So let's see. I've explained all this. Now, if you have adjacency matrix for non-directed graphs, the type of graph that we're going to get now will be symmetrical. Why are we saying this? If you have edge, let's say AB, AB here is the same as edge BA. So whatever you give to AB, do the same thing to BA. And the value that you give to AB, the same thing that you give to us, BA, because the graph is non-directed. But when it is directed graph, that's why you are not going to get symmetric what? Matrix. You're not going to get a symmetric matrix. So let's move on to this example, and that's why we're able to see how we can now form adjacency matrix of a given matrix for a given graph. Now let's go to example number 4. Now let's construct an adjacency matrix for the graph chain, which is equal to VE below. So here we have this graph, and we are now going to find either 2 or more vertices are adjacent to each other. So we have to identify first with the vertices that we have. And we are vein 1 up to vein 4. So we are vein now from vein 1 to vein 4. Can you all see?
Yes, sir.
Yes.
So this was a non-directed graph. Therefore, if we stand on any vertex, then we try to see those that are connected or that are connected to that vertex, all the edges that are connected to that vertex. So, but we are now come out with the vertices here. So in the matrix, the first row here, we just write all that matrix in that order. We have V1, V2, V3, V4 on the first row. Now the first column to write the same vertex because we want to see if the two of them are adjacent to each other. If so, then we will make it 1. If not, then 0. But at times we have a vertex to another vertex, we may have 2 or more edges that connect them. When you have a multigraph, then that's why we count the number of edges that connect them and then we write it down there. It's okay. So are you okay with that?
Yes, please, sir.
Okay. So let's see, we are the vertices vein 1 to vein 4 on the first row. We are the same vertices because it's adjacency matrix. We deal with the vertices. Vein 1 to vein 4 is also here. So when I go to the second cell here, now this vein 1 and vein 1, is there any connection for vein 1 and vein 1? Is there any edge that connects vein 1 to vein 1? If yes, how many are there? If 1, 1. If 2, write the 2 down. So is there any connection between vein 1 and vein 1?
Yes, sir.
Where?
So the loop above vein 1.
Yes. So we're having a third loop here. That connects vein 1 to vein 1, and it's only one loop. Therefore, we have that one as 1. Then we keep on going to other vertices using the vein 1. Now, then the connection between vein 1 and vein 2.
Yes, sir.
Please, can you hear me?
Yes, sir.
Then answer
I
the
can
question.
hear you.
Then
There's
what?
a connection.
Then the connection.
Yes, sir.
So you have edge here that connects then what to do. So you have 1. Now then 1, then 3. Is there a connection here?
No, sir.
So give it 0.
Yes.
Then 1, then 4. Then a connection.
Yes, sir.
So you get that 1. So we are done with the then 1. Then you move on to the next vertex, which is then 2, and do the same thing for all of them. So then 2, then 1. Then 2, then 1. You have
Yeah,
edge.
there's
sir.
a connection. Yes, sir.
There's
So you
one.
get 1. So 1 here. Then 2, then 2.
There's
Since
no
there's no
V2.
self loop here, so you don't have
There's
the
no
edge that connect then 2 to
V2.
itself. Therefore, get 0 there. Then 2
Okay.
to then 3.
And there's a connection.
There's connection.
So therefore, you get 1. So 1 here. Then 2 to then 4.
There's no connection.
So 0. Then you move on to the next vertex, then 3. So we have then 3, then 1 is 0. Check that. Then 3 to then 2 is 1. That's the edge. So you have 1 there. Then 3 to then 3, no self loop at the then 3. So it's 0. Now you are then 3 to then 4. When you look at this, these vertices, there are 2 ways that you can move from then 3 to then 4. One is by this straight line here, or straight edge here, and one is by this arc. So therefore, we have 2 edges that connect then 3 to then 3. Therefore, hence we have 2. Can you see it?
Yes, sir.
Are you following?
Yes, sir.
Sir, following, sir.
Okay. So let's do the same thing to then 4. Then 4. So then 4, then 1, it's 1. Then 4, then 2, no connection to 0. Then 4, then 3. That 1, 2, we have then 4, you have then 3. We have 2 ways or 2 edges. We have that 2 here. Then we have then 4, no self loop at the then 4, so 0 there. Now, if you have a graph without any self loop at any of the vertices, then the diagonal of the adjacency matrix are all 0. So that's why we are doing 1, because we have the self loop at the then 1. That's why we have here to be 1. Other than that, here should also be 0. Are you okay with that point?
Yes, sir.
Yes, sir.
Yes, sir.
Then
Please,
again, I
I
said if you have non-dilated graph, then the adjacency matrix should be symmetrical. Let's check if it's true. Now let's go to V1, V2, it's 1. Therefore, V2, V1 must also give you 1. So you have V2, V1 is also 1. It's okay, that is symmetric. V1, V4 is 1. Therefore, you have V4, V1 must also be 1. So V4, V1 should also be 1. Is okay?
yes, sir.
Yes, sir.
Now, V3, V4 is 2. Therefore, V4, V3 must also be 2. Because it is non-dilated graph. Hence, the adjacency matrix must be symmetrical. Any question? Okay, if no question, let's move on to the diagram. The diagram. Example number 5. The same principles. But you know, when we're dealing with the what? In degree and out degree, the same principle is going to apply here. So let's check the example 5 and see. Now you are having 5 vertices. So we have V1 up to V5. So just draw the array here. Then you fill in the set depending upon the condition between or the connection between the two edges at a given point. So no subloop, therefore all the diagonals must be zeros. So let's start with vein 1 to vein y. It's no subloop, so 0 there. So let's go back to vein 1 to vein 2. Vein 1 to vein 2. Now you don't have connection from vein 1 to vein 2, but you are V2 to vein 1. Is it okay?
Yes, sir.
Now you don't have the edge that starts from vein 1 to vein 2, but you are the one that starts from vein 2 to vein 1. Therefore, your vein 1 to vein 2 is 0. Vein 1 to vein 3, no connection, so you get that all those 0 there. Vein 1 to vein 4. Now you are having the arrow that starts from vein 1 and ends at vein 4. Therefore, you have 1. So vein 1, vein 4 is 1.
Okay.
Vein 1, vein 5 is 0. Though we have vein 5, vein 1. Not vein 1, vein 5. So that will give us our second row entries at this. I hope you're all following.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Yeah.
Now let's go to vein 2. We are done with the vein 1, so let's go to vein 2. This is our vein 2. And start from vein 1. Vein 2, vein 1. Do you have a connection?
Yes, sir. What, sir?
Yeah,
Yes,
the
sir,
arrow
1.
moving from vein 2 to vein 1. That will be 1.
Yes,
Now
sir.
you see that vein 1
Yes,
to vein
sir.
2 is 0, but vein 2 to vein 1 is what? 1. Therefore, for a digraph, it's not symmetrical. Digraph is not symmetrical. Vein 2 to vein 2, no loop here, so therefore that one is also 0. Vein 2 to vein 3, what are you going to get?
0. 0.
Vein 2 to vein 4,
0.
0.
vein 2 to vein 5,
1.
1. Good. So we get this.
You have
We
1.
do. And this. Go to inventory. So try to get fill it. We are not going there and then we fill it before you come back to this table to check whatever you have gotten. Are you okay? So you can just draw your own thing and just be filling the rest. So we are vein 3, vein 1. The fact, vein 3, vein 1.
0.
Vein 3, vein 2.
1. 1.
Vein 3 to vein 3 is what?
0.
0.
To vein 4.
1.
1.
1.
To vein 5.
0.
0.
So we are done with the vein 3. Let's go to vein 4. Vein 4, vein 1.
0.
0.
To vein 2.
0.
To vein 3.
0.
0.
To vein 4.
0.
0.
Vein 5.
0.
0.
So we are done with that one. So let's go to the last vertex, vein 5. Vein 5, vein 1.
1. 1.
Vein 5 to vein 2.
0.
0.
Vein 3
0.
1.
to
1.
vein 4.
1.
1.
1.
To vein 5.
0.
Good. So let's compare what you have gotten to what we have it on this slide. So check. Is that okay?
Yes, sir.
Any question on that?
There is no first one.
Okay, then let's go back so that you try some of them. The previous graph that you have seen. Let's go back so that you get try some of them. So you are not going to do it yourself.
Sir, please, I have a question.
Ask.
The loop on the second example, there's a circle, but you said it's not a loop. So if there's a loop, would the question state it?
No, it's similar to this one. They are not loop, they are just vertices. Again. But because I just wanted to write the vertex inside, that's why I'm using this for the circle. And there's a loop, you see there's a point. See there's a point, maybe a point here.
Okay. Okay.
So see that connection there. They
Okay.
start from one end and you end at the other end or that vertex.
Okay.
So these are just vertices.
Okay.
Okay.
Okay, sir.
Another question, please. Then let's try this one on our own. Let's try it. Just 2 minutes to do this one. Okay, so let's go to the second rule. V1 to V1.
0.
Okay, V1 to V2
1.
1.
to V3
0.
to V4.
1.
We are done with the V1. Let's go to V2. V2 to V1. V2 to V1.
0.
To V2
0.
to V3
1.
to V4.
0.
Okay, let's go to V3. V3 to V1.
1.
V2.
0.
V3.
0.
V4.
0.
Good, you are doing well. The last vertex. V4 to V1.
0.
To V2.
1.
V3
1.
to V4.
0.
That's good. You are done well. So that's how you can draw the adjacency matrix for diagram. Let's try one for non-directed graphs. Try this one also, 2 minutes. Okay, let's start with the V1. Get what the matrix. V1 to V1 is what?
0.
To V2.
0.
I could see that V1 is an isolated vertex. Is that not true?
Yeah.
So what it means for V1, there's no connection to the other vertex. Therefore, the row for that V1 will be 0 throughout.
Yes, sir.
And the columns under the same V1 will also be 0 throughout. You agree?
Yes, sir.
Good. Now, if you go to V2, it is also pendant vertex to a degree of 1. Therefore, there's only connection with V3. Is that not true?
Yes, sir.
So therefore, V1, no connection to the V2. V2, no connection to the V2 itself. Then we have only one connection with the V3. The rest will be 0. I'm sure you're checking it.
Yes, sir.
This is having 2 connections. One with the V2 and one with what? V4. The rest will be 0. V4 is also having 2 connections. That with the V3 and the V5. Others will be 0. V5 is having how many connections?
3.
3 connections.